Now here we are going to see a problem from the topic welded joints. Let us see the problem. A bracket carrying a load of 15 kilonewtons is to be welded as shown in the figure. Find the size of the weld required if the allowable shear stress is not to exceed 80 megapascal. So this is the bracket which is attached to one more plate by this arrangement welded joint, and here 15 kilonewtons is acting like this, and it is which is making an eccentricity of 125 mm from the center of gravity, and the width of the bracket or width of the plate is given as 80 and length of the weld is given 50 here. So if you see the given data, load on the bracket 15 kilonewtons, that is 15 into 10 to the power of 3 newtons. Allowable shear stress 80 megapascal, that is 80 Newton per mm square. Width of the plate or bracket is given be 80 mm and length of the weld 50 mm. We have to find out the size of the weld. So here, to find out the size of the weld, first of all let us assume or let us analyze what this force will do to this weld system. So this force is acting here like this, and this will produce a direct or primary shear stress in the weld sections, and also because of eccentricity of loading about center of gravity, it will produce a secondary shear stress in the weld section because this load is trying to rotate this bracket about the center of gravity. So in that process, when it is rotating about the center of gravity, so a shear stress is produced in the weld sections at so many points. So here the load is trying to produce primary and secondary shear stresses in the weld portions. So here if you see, so that we have to find out direct or primary shear stress. Let us take tau 1 and secondary shear stress tau 2, and we find these two in terms of S, and we'll find out resultant between this tau 1 and tau 2 by using this formula, that is tau is equals to tau 1 under root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta, because this tau 1 and tau 2 will be acting as a two sides of a parallelogram. So we'll use this parallelogram formula to find out the resultant between tau 1 and tau 2, and we'll substitute this tau 1 and tau 2 in terms of S here, and this is the allowable shear stress in the weld material which is given as 80. So we'll solve this equation to find out the S. So this is we'll do to find out the size of the weld. So in the first step, we have to find out direct or primary shear stress. We know the formula, basic formula, that is shear stress is load by area. So see here what is the area which is getting affected because of this load applied. So if you see, this is the weld section, and if you see in the side view, this is a triangular section, cross section of the weld is triangle, and if you see, this is called size of the weld or leg of the weld, and if you take this is the critical section which is called throat, and if you take the area along this throat which is called the critical area, that is throat area, where you will get the maximum stress. So that area only have to take here, because maximum we have to substitute the area which is taking the maximum shear stress, or where you are getting maximum shear stress. So that is throat thickness into length, you will get the rectangular area. So because there are two weld sections are there, so you will multiply with 2, and this throat thickness is given by 0.707 times of S. If you see, if we draw a big diagram here, this cross section of the weld, so this is the cross section of the weld triangle. Suppose this is the throat here we have taken, and this is the size of the weld S. So we know this is a 90 means 45 45, and this is 90, and obviously this will become 45. And from this triangle, from the small triangle, if I write sine 45, so this will be opposite by hypotenuse T by S, and T I can write S into sine 45, or this T as 0.707 times of S approximately. So that is we have written here into L, and L is given length of the weld is given 50 mm in the question. So we have written here, and if you simplify that, you are getting it as 70.7 times of S mm square, that is the area. And if we substitute in this formula, tau 1 is equals to P by A, that is 15 into 10 to the power of 3 by 70.7 S, and if we simplify that, we are getting 212 by S Newton per mm square. This is the direct or primary shear stress. And if you go for to calculate secondary shear stress tau 2. So if you see this diagram, this I told this load is also trying to produce secondary shear stress because it is rotating about the center of gravity. So in that process, it will produce secondary shear stress at so many points in that weld sections. And here we have to take where we are getting the maximum secondary shear stress. So this magnitude of the secondary shear stress is proportional to the length between the center of gravity and the point where we are taking that secondary shear stress. So by observation, we can say that at this point we will get the maximum secondary shear stress. Why? Because from center to this point we will find the more length. Suppose in this direction, if we take these corner points, we will get the more length. So any one corner point we are selecting such that this length will become maximum. So this point will become critical point or point where we are getting the maximum secondary shear stress. So we should design for maximum stress only. So such that and magnitude is proportional to this length. So this length is more, so tau 2 is more, we will get maximum secondary shear stress, and the primary shear stress is vertically downwards tau 1, and this tau 2 direction will be perpendicular to this line joining like this in this direction tau 2. So this tau 2 we have to find out. So to find out tau 2 in this case, we have the formula, that is P into E into R2 by J. So where P is load acting and E is the eccentricity value, and R2 is this distance from center of gravity to this point that we are taking it as, let us take it as R2, and J is polar moment of inertia that we will see. And first of all, if you want to find out R2, so if you observe this triangle A, B, G, so this will become hypotenuse, and we can write R2 is equals to under root of AB square plus BG square from this triangle, and AB is nothing but 40. How means from here to here it is 80 given, so this AB will become half of this, that is 40, and BG will become half of this 50. So because this is total and because this is center of gravity and this some like looking like some rectangle, so half of this is BG, that is 25. So AB is 40 and BG is 25, and let us take this BG as R1, and this is AB 40 we got and BG 25 we got. Substitute here 40 square plus 25 square, and if we solve it, we are getting this R2 as 47 mm. And why we have taken this R1 means to calculate this theta, we require theta also to find out the resultant shear stress at this point. So if you observe this triangle, theta is the angle between the primary and secondary shear stresses. So if this is theta, this is 90 minus theta. Why? Because this total thing is 90 degrees. So I told this secondary shear stress is perpendicular to this length, means so this is 90. So when this is 90, this will become 90 minus theta. When this is 90 minus theta, obviously this is theta to satisfy this total angle of the triangle is 180. So this is 90, and if this theta, this is 90 minus theta, and if this is 90 minus theta, this is theta, and this is 90, such that we are getting total angle in the triangle is 180. So such that it will become theta here, and if you write cos theta adjacent by hypotenuse R1 by R2, so we have assumed here it is as R1, BG as R1, that is 25 here, and R2 we got 47 here, and if you simplify that, we are getting cos theta as 0.532. And here we have to find out J, that is polar, J is called polar moment of inertia of this weld section about the center of gravity. For that J, we have the formula T into L into 3B square plus L square by 6. T we got 0.70 times of S, L is given 50, and B is 80, L is 50, and it is by 6. And if we simplify that, we are getting J as 127,850 into S, that is mm power 4, polar moment of inertia. Units are mm power 4. So to find out tau 2, substitute these values. We have already seen this formula, P into E into R2 by J. P's load, that is 15 kilonewtons or 15 into 10 to the power of 3 newtons. E is the eccentricity, we have seen it is 125. If you see, this is the eccentricity, this is 125. Load is 15 kilonewtons. And so this is P 15 into 10 to the power of 3, E 125, and R2 we got 47, and J it is 127 850 into S. And if we simplify that, we are getting tau 2 as 689.3 by S Newton per mm square, secondary shear stress, and cos theta we have calculated 0.532. So if you substitute these values in the resultant shear stress equation, so I told tau 1 and tau 2 are, so here tau 1 and tau 2 are, if you assume these are two adjacent sides of a parallelogram, so to find out resultant between these tau 1 and tau 2, we can apply parallelogram law. So according, we can write the resultant equation as under root of tau 1 square plus tau 2 square plus 2 tau 1 tau 2 cos theta. So when you assume P and Q are the adjacent sides, so we can know the formula P square plus Q square plus 2PQ cos theta. Same that we have written tau 1 and tau 2 here. So tau 1 we got 212 by S, and this is 689.3 by S, and 2 times of this tau 1 and tau 2 substituted, and cos theta 0.532 substituted. And if you simplify that, and we are equating this resultant shear stress to the maximum allowable shear stress, that is 80, to maintain the equilibrium or to avoid the failure. So we are equating the allowable shear stress in the weld section or weld material. So if we simplify that, we are getting the size of the weld as 10.3 mm. So this is the way to solve this kind of questions. So for more videos, please subscribe and activate bell symbol. So please like it, share it with your friends, and don't forget to subscribe. Thanks for watching.